Hello, I'm Mark Lundstrom. I'm a professor at Purdue University, and I'd like to tell you about this course on semiconductors that I'll be teaching. So first of all, let's talk about what is a semiconductor. We're familiar with metals. Metals are good conductors of electricity. We also know about insulators. Insulators are poor conductors of electricity. A semiconductor is right in between. It's not a good insulator. It's not a good conductor. So what is it good for? Well, it's good because it has a remarkable property. We're able to control the properties of semiconductors by introducing small numbers of other atoms into them. This is called doping, and it allows us to make the semiconductor a good insulator or a good metal or anywhere in between. And that ability is the basis for all electronic devices. And electronic devices are everywhere. They're in the cell phones that we carry around, in the cell phone towers that relay communications, in solar cells that convert sunlight to electricity, in communication satellites that relay signals around the globe, in displays, in our headlights and taillights, and all over the place. So semiconductors are everywhere. It's hard to imagine the modern world without them. So if we look at where things are going in the 21st century, it's going to be even more exciting and even continue to be powered by semiconductors. So today we're talking about the Internet of Things, self-driving vehicles, robots, virtual reality, data science, lots of software. All of these applications are enabled by semiconductor technology. Now, Bob Luckey, a famous electrical engineer, points out that we can think about this in a pyramid. There's a lot on the top of the pyramid, but it's all enabled by a small group of companies and individuals that are involved in semiconductor manufacturing. That small group of companies and individuals enables all of these things that we see every day. In between the tip of that pyramid and the higher levels where all of the applications live is an area where a group of individuals who understand the underlying technology but understand the applications and the needs of those applications. And those are people that are able to put the technology and the application together in unique and creative ways. You may be one of those individuals, and that may be a reason for taking this course. Or you may be one of the chemists or physicists or material scientists involved in manufacturing semiconductors, looking for a broader understanding of what all of this means in terms of the applications of what you're doing. I want to remind you that this is not a course about semiconductor devices. It's a course about semiconductors. It's about the background that will allow you to understand the operation of any device. We'll be talking about chemistry, material science, solid-state physics, and quite a lot about electrical engineering. The course consists of 5 units. The first is on material properties and this concept of doping. The second is an introduction to quantum mechanics, which becomes important in devices. The third is how we calculate the concentrations of positive and negative charge carriers that make devices possible. The fourth is about how those charge carriers move, how they're generated, and how they recombine. And the fifth, we put it all together in a set of mathematical equations that describe the operation of virtually any semiconductor device you can imagine. And in that fifth section, we will conclude by introducing a very powerful conceptual approach for solving those equations without mathematics. And this consists of drawing what we call an energy band diagram. This is something that began right at the birth of semiconductor electronics with one of the inventors of the transistor. And it's a very powerful way of qualitatively understanding how a semiconductor device works simply by sketching a diagram and without solving the mathematical equations. So we'll end the course with that. So this course will give you the background that you need to understand the operation of almost any semiconductor device you'll encounter. The course will be largely descriptive with physical explanations, but it provides a starting point for those of you that would like to dive in deeper. It's a summary of the way that electrical engineers have learned how to think about semiconductors over the decades during which they've been invented, developed, and enhanced. But it's also informed by recent advances in nanoscience over the past couple of decades. And finally, I'll mention that it's a part of a new initiative here at Purdue, an initiative we call Breadth at the Edges. This is a set of courses that are designed to provide people who are experts in one aspect of technology with the breadth they need to work on teams with other experts. So I look forward to seeing you in the course.